Okay, welcome. This is the homework from page 162 on the chain rule, and this was the homework that was due the Friday of the last day of school for period 3 and 6, but we did not go over it in class, and the homework that was due on for period 4 was due later. Anyway, I said for you to do this first. These problems are still basically just do the chain rule problems. So this would be a good time to totally master your understanding and ability to execute the chain rule. Alright, so I'm just going to do kind of all of these, I guess. Maybe not all of them, we'll see. Since you can skip through. Okay, here we go. 51. Find the slope of the tangent line to the graph of the logarithmic function at the point 1, 0. So the curve is ln of x cubed. Yeah. And we want to know the slope of the tangent line at the point 1, 0, and there's this little picture. Of course, every log function kind of looks like that. So what is the slope of the tangent line here at 1, 0? That's what is being asked. Okay, well, this is not so hard. Probably what I would do here is I would actually apply a log rule, which says that this is 3 ln x. And now when I go to take the derivative, I get that this is just 3 over x. And therefore, the derivative at that point is 1, 0. So the derivative at x equals 1 is just 3. Okay, and, well, whatever. That's all I got. Is that right? Of course it is. Okay, good. That problem was boring. One down, like a bajillion to go. Here we go, 85. 85 says the curve is y equals ln of x root x squared minus 1. Yeah. Alright, so and the problem I think just says differentiate. Yeah, that's it. Okay, well, what should we do? First of all, we should be happy that there's a natural log here because it means we can break this up into little pieces. And so the first thing I'll do is I'll apply a log rule. Ln of AB is ln of A plus ln of B. So this is ln of x plus ln of, but this is really x squared minus 1 to the 1/2. And that means that this is really ln x plus 1/2 ln x squared minus 1. And so I really don't need to use any kind of product rule, chain rule, really much here. Well, I don't need to use a product rule at least, because now when it comes to differentiating, we did this in class the last week we were in school. This is now easy. This is 1 over x. And this is 1/2 times the derivative of ln of something is 1 over the something, back inside for the derivative of something. So that is 2x. And that's probably what you'll see in the back of the book is 1 over x plus x over x squared minus 1. Maybe they get a common denominator, but that doesn't seem important. All right, doing all the homework. 87. This is just another problem. This basically the same thing. Not even sure we need to do this one. Ln of x over x squared plus 1. Okay, so what do? We use the log rule to write it as ln x minus ln x squared plus 1. And then becomes easy to differentiate. It's 1 over x minus the derivative of ln of something is 1 over the something back inside for the derivative of the something. Okay, 92. What's going on in 92? This is just more of the same, man. This is just y equals ln of x minus 2 over x plus 2. But all of that is being cube rooted, so that's really 2 to 1/3. So the professional way to do this is to apply log rules. So this becomes 1/3 ln of x minus 2, x plus 2. but then that's really 1/3 ln x minus 2 minus 1/3 ln x plus 2. And so we see, once again, that logarithms are great because now things are broken up into little pieces and we can just differentiate easily. So this becomes 1/3 x minus 2 minus 1/3 times the derivative of ln of x plus 2 is 1/x plus 2. And then back inside, but that's just 1. Okay. Alright, so that was just like 4 or 5 of the same problem. Here is another one. This is saying what is y equals ln of the absolute value of sine x. Okay, so this absolute value may have given you some strange pause here, and this is not something I did in class, so I'll just do this now, really fast. This is maybe not the most important thing in the world, but it is something that comes up kind of a lot, so let's talk about it now. The absolute value is strange. In fact, we know, that a function like absolute value x is sharp at 0 and doesn't have a derivative. So perhaps you should be scared of absolute value when it comes to calculus or something. Well, I think that what we should do is just look at, just take the ln of absolute value function as it is and try to understand it. Well, what is the ln of the absolute value of x? Well, we can make maybe a graph of this. What does the graph look like? Well, if x is positive, then the absolute value of x is just x. In other words, absolute value of x is just, well, okay, so when x is positive, it's going to look exactly the same. And actually, maybe we should just do it out, right? What is the absolute value of x? It's just x when x is greater than or equal to 0, and negative x when x is negative. This is how we deal with absolute values in calculus. We get rid of them. So if I want to analyze ln of the absolute value of x, then I just do it in cases. This just is, well, it's ln of x if x is positive, because that's just the definition, and if x is negative, then, these are commas, then it's just ln of negative x. Okay, so we see that the ln of the absolute value of x function is kind of like an extension of the natural log function. Now, the domain of this function is not just positive numbers. As we see, it's for positive x, it's just the same, but for negative x, it's ln of negative x, and ln of negative x is just ln flipped over the y-axis. And so what we have is like a this type function whose domain is all real numbers except 0. Okay, well, if that's what natural log of absolute value is, then what is the derivative of ln of the absolute value of x? And the answer is, well, we should just take the derivative of this piecewise function. So I want to take the derivative of ln x when x is positive, and I want to take the derivative of ln of negative x when x is negative. But of course, here we just get 1/x when x is positive. And here we get, what is the derivative of the ln of negative x? Well, I have to use the chain rule. And so the derivative of ln of something is 1 over the something, but then back inside for the derivative of negative x, which is negative 1. So it's also just 1/x. In other words, the derivative of the natural log of the absolute value of x just is 1/x. Okay, that's maybe a little bit like boring or something, yet when we go to sort of try to understand it graphically, we see it makes complete sense, right? Because if you look at natural log, if you look what the derivative should be, it should be a huge positive number, and then it should be around here about 1, and then here a smaller positive number thereafter. So something that looks a lot like 1/x. But now ln of absolute value of x when x is negative is now going to be a tiny negative number, and then about -1 here, and then negative infinity. So something like that. And so 1 over x is a very plausible answer for that. Okay. So understanding this now as kind of just a rule that ln of absolute value of x, that the derivative of it, I'm writing this in purple now, is just 1 over x, means that wasn't much to do in this problem. Here we just say, okay, well, the derivative is then, the derivative of ln of the absolute value of something is just 1 over that something, back inside for the derivative of the something, the derivative of sine is cosine, and so it's just, actually it's just cotan. Okay, and then, la 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 la, that was 95, I guess. Sorry, got distracted. Yeah, that's right. 98 is a strange problem. The function is given to you as y equals ln of the absolute value of secant x plus tan x. Okay, well, once again, I think the thing to do is just do it. So what is the derivative? Well, it's going to be 1 over ln of that. The derivative of the ln of the absolute value of something is 1 over the something back inside for the derivative of secant x plus tan x. And the derivative of secant, I just know this, is secant x tan x. So secant x tan x. And the derivative of tan is secant squared. But now, if you factor a secant out of the top, then that becomes tan x plus secant x. Oh, that's like kind of interesting. That cancels. And so this whole problem is just secant. So okay, stick that in the back of your mind somewhere, that this very strange function, this number 98, if you differentiate it, you in fact, you just get secant. Okay, all of those were kind of similar little problems. Let's erase and then just keep on going. Oh man. Hopefully you guys find this helpful to watch for help going over this homework, but hopefully you're skipping around or watching it on 2 times speed or not watching it at all. Here we go. And also a baby could scream at any moment. Here is, why did I assign this problem? This just looks really annoying. Here's this function. It's 3 plus 2x times e to the negative 3x. And believe it or not, we need to find the second derivative. Okay, so this is just an exercise in chain rule and being careful. Let's go. We're going to take the derivative of this. Well, it's the derivative of the first, which is 2. Times the second, so times e to the negative 3x, derivative of the first times second, plus the first, 3 plus 2x, times the derivative of the second. And what is the derivative of e to the negative 3x? Well, it's e to the negative 3x back inside negative 3. Do the first, I'm now just double checking, do the first times the second, plus the first times the derivative of the second. So that's interesting because I can factor out an e to the negative 3x, and when I do so, I'm left with 2 plus negative 3 times 3 plus 2x. In other words, e to the negative 3x times negative 6x minus 7, I guess. Yeah. And I wish I could just stop there, but the problem said to find the second derivative, so I just kind of have to do this all over again. So now it's I'll do it this way. So the derivative of this one is negative 6 times e to the negative 3x plus derivative of this times this plus this times the derivative of that, which we know to be e to the negative 3x back inside negative 3. And so once again, I'll factor out an e to the negative 3x, and I'm left with negative 6 plus, distributing the negative 3, that's 18x plus 21. And so I guess my final answer should be e to the negative 3x times 18x plus 15. I have no idea if that's right. I have no recollection of ever doing this problem before. Live on camera, we're gonna just check the back of the book. This is riveting. Oh my god. Maybe this is dumb. Surely I am right. Incapable of error. I am. Yeah. Woo! Okay. Good. More. 123. 123 just says that f of x is 4 to the x, and it just says, dude, take the derivative. Okay, so depending on your personality, you either immediately memorized this rule, or you don't memorize anything and you look it up, or you rederive it on the spot, which is, I think, the best option when you can't remember. So for those of you who know the rule, then you just know it, and this is a 5-second problem. Derivative of 4 to the x is just ln 4 times 4 to the x. And eventually you'll just learn that, but if it's been a while, like a couple of weeks, and you completely forget why this is true, you can just redo it. So how do we do this? Well, if y is 4 to the x and I want to find the derivative, first just note that dy dx is the thing that I want, right? The derivative of y with respect to x. Okay, how do we find it? It's the same story every time, right? There's an x up here high, and we need to bring it down, therefore we need logarithms. So we take the logarithms of both sides, and thus we get ln y equals x ln 4, and now that the exponent has been brought down, we can differentiate normally. So we're going to take the derivative of both sides with respect to x, differentiating implicitly, and when we do this, what happens? Well, the derivative with respect to x of ln y is 1 over y back inside dy dx. And here, the derivative of x ln 4, ln 4 is just a number, so the derivative of ln 4 times x is just ln 4. And thus, I have sort of reproved that dy dx is in fact y, otherwise known as 4 to the x, times ln 4, which is what I said over there. Okay, and 125 now is like a follow-up problem, which says, well, okay, it's not a follow-up problem per se, but it's just another problem, 5 to the x minus 2, and I need to find the derivative. So, okay, so at this point, let's just say that we've internalized now that the derivative of 5 to the something is just ln 5 times 5 to the something. Back inside for the derivative of x minus 2, which is just 1, and so we're done. Alright, just moving right along. 126. This is a bit of a drag. Y equals x times 6 to the negative 2x. Okay. Well, I have to do, I'm now going to just take, and this is why I think it's useful, I'm going to take the above derivation as just now like a proof of a general rule for differentiating 6 to the something. And I have to do the chain rule inside of that, and then there's also just a product rule situation here. So being kind of careful, what this says is that the derivative of this must be, well, it's the derivative of the first, which is 1, times the second, plus the first, so x, times the derivative of the second. So now I need to differentiate 6 to the negative 2x. How do I differentiate 6 to the negative 2x? Well, the derivative of 6 to the something is ln 6 times 6 to the something, but then back inside for the derivative of negative 2x, which is negative 2. Okay, and probably you could stop there, or the back of the book, surely factors. So if you factor out a 6 to the negative 2x, then you're just going to get something like 1 minus 2 ln 6 times x. Something like that as your final answer. Okay. 131, 135. Oh my gosh. 131 is y equals log base 3 of x. Okay, well, once again, maybe you've just memorized this rule, but we can rederive it. How? Just by 3-upping both sides. So this is 3 to the y equals 3 to the log base 3 of x, which is, by the definition of logarithm, these are inverses of each other, that's just x. And now that I've sort of rewritten this as 3 to the y equals x, that's kind of the definition of logarithm, then I can to take the natural log of both sides. There's really only one logarithm, the natural logarithm. So if I take the ln of 3 to the y, and over here that's ln of x. Okay, well now I apply the log rule that's y ln 3 equals ln x. And now that I've brought everything sort of down, I differentiate both sides with respect to x. So if I take the derivative with respect to x of ln 3 times y, and over here I take the derivative with respect to x of ln x. Okay, trying to squeeze this in now. What is the derivative with respect to x of ln 3 times y? Well, it's just ln 3 times, and here we just get dy dx. But over here I get 1 over x, and that proves that dy dx is 1 over ln 3 times 1 over x. This is almost exactly what I did in class when we were back at school that last week. This is sort of the repetitive explanation of that method for differentiating logarithms of other bases. Okay, and then 135 is just like more. I'm just essentially just doing this entire homework. It's kind of silly. Oh well. So this is y equals log base 5 of root x squared minus 1. Okay. Well, I'm now just going to take this as a general rule that I just know, man. Actually, here, I'm going to do even something else first, which is think of this as log base 5 of x squared minus 1 to the 1/2, so that I can apply a log rule. So this is really 1/2 times log base 5 x squared minus 1. And now I will differentiate. Well, being very sort of careful here, I realize, okay, first of all, the derivative of 1/2 times something is just 1/2. And the derivative of log base 5 of x squared minus 1, okay, well, let me just kind of know that the derivative of the log base 5 of something is 1 over ln 5 times 1 over something. Back inside for the derivative of the something, which is 2x. So it is helpful to kind of have these things not necessarily memorized, but at least like chunked in a kind of way such that you can just apply the rule. Okay. Final answer would be 1 over ln 5 times x over x squared minus 1. The 2's cancel. Okay. Boom, boom. 1, 2, 3, 5 problems to go. I don't even want to do 145. It's kind of boring. I don't want to do it. I guess I can do it. Okay. 145. It just gives you a bunch of data. Let's see. G of 5 equals -3. G prime of 5 is 6. G prime of, H of 5 is 3. H of 5 is 3. And H prime of 5 is -2. h prime of 5 is negative 2. And I think it's going to say something like, oh, do you even have enough information to do this problem? And I think for at least one of them the answer is no. Okay, so let's just do this really fast. Here we go. Part A says, for each of the problems we want to find f prime of 5. Okay, so f is g times h, I believe. G times h. Okay, so I certainly know how to differentiate this. It's just the product rule. So it's derivative of the first times the second plus the first times the derivative of the second. And now if what I really want is f prime of 5, then I just stick in those things, right? G prime of 5, 6, h of 5, 3, g of 5, negative 3, h prime of 5, negative 2. And so the answer should be 18 plus 6 equals 24. Okay. Others. Others. 146B. Oh no, sorry. We have to do all the rest of these. Okay, B. B now is a chain rule situation. So we have F is G of H of X. And so what is F prime? Well, according to the chain rule, it's G prime of H of X. Back inside for the derivative of H, so that's H prime. Okay, so that's fine. But now when I go to do F prime of 5, then I realize that that is G prime of H of 5 times H prime of 5. And according to my information over there, I know exactly what H of 5 is. It's 3. So that's G prime of 3. And here H prime of 5 is negative 2. But now I have to just stop the problem because I was only given information about G and H, their value at 5 and their derivative at 5, but I just don't know what G prime of 3 is. So this is just information I don't have. So this was a kind of a, I guess you call it a trick or something. We can't do this problem because we weren't given that information. That was one of the possibilities. Okay, and I guess this is just gonna happen again. For C, we get that F is G of X over H of X, and now we take the derivative. Okay, so this is basically just asking us to practice the quotient rule. So it's the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. Boom. Okay, and so therefore, when it comes to doing f prime of 5, I just plug those in. So G prime of 5, 6, H of 5, 3, minus G of 5, negative 3, and H prime of 5, negative 2. And then all over H of 5, which is 3, so that's all over 9. So it's just going to be 18 minus 6 is 12 over 9, so 12 ninths or 4 thirds. Okay, and I think part D actually I can do because D is the function f is g of x quantity cubed. I think I can do this because when I go to take the derivative, the chain rule says that the derivative of something cubed is 3 something squared back inside for the derivative of the something. And so now, so that's the general rule, but now if I want to do f prime of 5, g of 5 is negative 3, so that's 3 times negative 3 squared times g prime of 5 is 6. And so that'll be something 162, I guess. 9 times 2, 27 times 6. Probably that's right. Okay. good. 4 problems to go. 4 problems to go. Okay, 146b. Oh, here we go. This is just a cute little problem. We actually did something like this in class, but maybe only in some classes. F is secant squared, and g is tan squared. And the directions were, take the derivative and notice that they have the same derivative. Okay. Well, forgive me if I've already given this explanation for a different problem, at least in some of the classes, but the most mindless way to do this problem is to just do it. So this secant squared should be parsed as, secant squared, and tan squared really means like tan quantity squared. So when it comes to doing the chain rule, the outer function is the squaring function, so okay. We go to do the derivative, and the derivative of something squared is 2 something back inside for the derivative of secant, and I just know that the derivative of secant is secant tan. Okay, and so what I get for the derivative of f is 2 secant squared x tan x. And when I go to take the derivative of g, I get, well, the derivative of tan squared, the derivative of something squared is 2 something back inside for the derivative of tan, which is secant squared. And so these two just are the same. So the problem is just over. But you should possibly wonder, what is the significance of these two functions having the same derivative? I think this just happened in the video that I made you guys watch. So yeah, I just do this really fast. What does it mean if two functions have the same derivative? It must mean that they're doing the exact same thing at the exact same time. And if the derivative represents the rate at which the function is changing, then if two functions have the same derivative, then it means that at every possible x value, they are both increasing or decreasing at the exact same rate, which tells you that the functions are kind of moving in sync with each other, although the actual proof of that is tricky. It's clear that if you have two functions, f and g, which are basically the same, but one is just been moved up, or they differ by a constant, then it's clear by just differentiating both sides that when you take the derivative of the left, you get f prime. When you take the derivative of the right, well, since the derivative of a constant is 0, then you get that. And so the logic says if two functions differ by a constant, so if you have some two functions f and g, and the gap between them is just c, then of course that they have the same derivative. The slope of the tangent line should be the